All right, so our topic today is water pollution, where it comes from, what kinds there are, and what it does, its sources, types, and effects. And so we're talking about water quality issues here instead of quantity issues, although the water quality can become worse depending on how much water there is. So in a drought, we could concentrate pollutants to the point that they became dangerous, even if they weren't dangerous when, for example, a reservoir was completely full, it might dilute those pollutants. So water quantity can influence water quality, but really we're going to focus on the quality. And so pollution could be a chemical change in the water, a biological change, or a physical change that has a harmful effect on living things. Or perhaps it makes it unusable for people. It could also be harmful for people. So we count as living organisms. So this could be a harmful effect on us or on other wildlife. And first of all, I think we've talked about this before. Let's just remind ourselves that there are these two major groups of water pollution. There's point source pollution that comes from a specific place. You can point right at it. So there would be some kind of pipe usually leading into the waterway, and you could say that is where the pollution is coming from, a specific point. On the other hand, a non-point source of pollution can't really be followed to a single location. So it's pollution that's widespread and is entering the body of water probably at multiple locations. So this could come from atmospheric deposition. So for example, this could be acid rain falling into a lake, or it could be smog that's dropping into a lake. In fact, we think one of the problems with Tahoe's clarity is smog that gets blown up here from Sacramento and then gets deposited into the lake. So then we also have runoff, where we have water flowing across the surface of the ground and picking up materials along the way. So it could be coming through an agricultural field and picking up fertilizers or pesticides. It could be flowing through an industrial zone after a rainstorm, and the water is it's got all the streets and parking lots are all wet, and it's dissolving any materials that are on the ground there left behind by the industry and carrying them into a river, lake, or the sea. And the same thing is true for residential runoff, where whenever it rains or when snow melts, it's going to carry whatever's on the street, it's going to carry it downhill towards the lake or the river. So it could be a point source or a non-point source. All right, then we have these major groups of water pollution, the major categories. So toxins are a wide variety of molecules that are poisonous to living things. Of course, the toxin would have to build up to a certain concentration before it was actually harmful, but it can directly kill creatures, or it can make them less able to fight off an infection, or it can weaken them to the point that it's easier for predators to catch them. So those are toxins. Acid rain, we've talked about before, that is arriving in the lake as a result of sulfur or nitrogen released from power plants and car exhaust. It then combines with moisture in the atmosphere, with water vapor, and it forms an acid that rains down on the lake or the forest. Next, and this is a big problem here in Tahoe, are sediments from construction or mining or logging. And so these sediments, just bits of sand and gravel and silt and clay, they're completely natural, but then we with these kinds of activities, we disturb the sediments, and that increases their buildup in the body of water. And it can build up to the point where it's harming that body of water. One example would be if the sediments buried a trout spawning grounds. So trout and salmon like to spawn in gravel, and if we bury that with sand or silt, then the eggs that the trout and salmon bury in the gravel, they can't get fresh water, they can't get oxygen, and then the eggs would actually suffocate. So that's one of the problems with sediments. Another one is that it can make the water look cloudy, and so that would go against our whole goal of keeping Tahoe blue by keeping it clear. We could have oil spills or leaks, and that would form that kind of shiny film on top of the water, and it can get in wildlife's fur and feathers and create problems for them. It might be a major spill like the one, the BP oil spill in the Gulf of Mexico, or it could be more minor things like people just filling up their boat with gasoline and they overfill the tank and it spills into the water. And that happens day after day after day and year after year after year, and then we have a problem. So these little things add up. Another category of water pollution is sewage. And I would add to this, not only from people, but I'm thinking about this more and more, but this is also from people's dogs. And it's also from cattle and hogs, especially where there's a feedlot where they have lots and lots of animals packed together, and they're kind of fattening them up just before they're going to send them to the slaughterhouse. And if they're giving them lots of food, then they're also pooping a lot, and that can put that animal sewage into any nearby bodies of water. So that's a problem. Fertilizers. So anytime we put fertilizer on our lawn, or a farm uses it, or they put it on a golf course, any excess fertilizer gets washed downhill in runoff. Both fertilizer and sewage would act in a similar way to stimulate algae growth. Another type of pollution, and this is one of the physical types, is heat. So when power plants and industries are using energy, they often end up producing waste heat that they have to get rid of. And a lot of times this heat is removed from the equipment by using a cooling system that pumps water through the equipment. And then that warm water is then put into a lake or a river or the ocean. And now we have this warm patch in that body of water. And one of the biggest problems with the heat is that the warmer it is, the less oxygen the water can hold. So as you heat up water, oxygen is lost from the water. It's able to evaporate more easily when it's warm. And so we have an area of low oxygen as a result of these power plants heating up water. And then a new source of pollution that we're just now realizing are pharmaceuticals and hormones that are coming from people's homes, often with their sewage. If people, for instance, have medication that they didn't take, maybe it's past the due date, or maybe they just stopped using it, sometimes to get rid of it, they flush it down the toilet. And people also end up putting hormones down the toilet in different ways as well. And these can have impacts on wildlife that are exposed to these drugs and these hormones. Are we good with that? Okay, so let's move on. This is a photo of a bacterial culture where we grow bacteria, and one way we can test to see if water is polluted or not is to look for what we call fecal coliform bacteria. So the most well-known one is E. coli. E. coli is a type of bacteria that normally lives in our intestines, and it lives in the intestines of other animals. So it's normal to have it there, but if it's in the water, that means sewage is getting in the water because it's coming from people's intestines or from cattle intestines. And that means other bacteria that could cause disease might also be in the water. It's not so much that the E. coli itself is a problem as it is that the other disease-causing bacteria that are with the E. coli could also be present. So we measure the E. coli, that's easy to do. And then if it's present, then we need to look more closely for other things like cholera and other kinds of disease-causing bacteria or parasites. We can look at these diseases that are passed through contaminated drinking water. It could be bacterial, it could be viral, could be from protozoans or from worms. So typhoid, cholera, dysentery, this type of hepatitis, another form of dysentery, giardia, and this parasitic worm, schistosomiasis, all of these are coming from sewage. And the way these organisms basically survive is they get passed from person to person in the water. So if we're not cleaning up our water effectively, then we're running the risk of getting any of these diseases. And this is really one of the main reasons that people have been able to have a growth in population is because we've fought off these diseases just by providing people with clean water. When we talked about how there was the medical technological revolution that allowed the population to explode, part of it was the technology of cleaning water so people weren't being exposed to these diseases, and so the death rate from these diseases dropped. Okay, here's a couple different sets of initials that we often use. They both involve oxygen, DO and BOD. So DO is dissolved oxygen, and the more oxygen in the water, generally, the cleaner the water is considered to be. And this doesn't matter if it's fresh water or seawater. If it has high oxygen, that's generally a good thing. Some fish and other wildlife can withstand low dissolved oxygen levels. Other fish require high dissolved oxygen levels. So things like catfish, they can do fine with low dissolved oxygen, but trout require high DO. And if you think about it, we can figure out how to increase dissolved oxygen just by reasoning our way through it. If the temperature is low, that means there's less evaporation, so the oxygen is staying in the water and not evaporating away. If the temperature is high, that means evaporation occurs easily and some of the oxygen is released into the air. And so high temperature water holds less oxygen. Splashing water, either from waves or from a river current, that increases dissolved oxygen because the water is actually interacting more with the atmosphere. So as the water splashes, it's going to pick up some water out of the air. But if it's not splashing, it's less likely to pick up water out of the air. This is one reason that many aquariums have a filter on the back that's kind of like a waterfall, because that helps dissolved oxygen get into the water by having that splashing action going on. Okay, another measurement of oxygen is biological oxygen demand. Now, while we want DO to be high for clean water, we want BOD to be low. The reason for this is it's a measurement of the amount of oxygen that is demanded, the amount of oxygen used by organisms in the water. And when there's polluted water, we often have overpopulations of bacteria that are decaying wastes, whether those are dead algae or sewage. If there's a bunch of bacteria in that water overpopulating it, then they're going to demand more oxygen. And so we have a high requirement for oxygen by these bacteria of decay. Because there's so many of them, that tells us there's a lot of nasty stuff in the water. So we want high DO, we want low BOD. Okay, and this is just a little graph showing the water quality for dissolved oxygen. Tahoe tends to be around here, 6, 7, 8. And you can see the higher the DO, the more polluted the water is. This is a pretty complex diagram that I'm going to skip for now. Okay, so when there's a river or a stream and we have a point source of pollution that's putting some kind of let's say a sewage pipe is going into the water, or maybe it's runoff from a hog farm, from all the pigs and their wastes that end up in the water. We can look at how the water is polluted right close to the source of pollution, but then it recovers downstream. And when we measure the dissolved oxygen, we end up coming up with what we call an oxygen sag curve. So here's the idea. What I want you to notice is this is a river flowing from left to right. So this is our oxygen sag curve. And right here we have a source of pollution. And this is some kind of pollution that increases the growth of bacteria, so they need oxygen to survive. And it kind of makes sense. Right next to the source of pollution, it's very polluted. And then as we go downstream, the water gets better and better, right? And let's look at this blue line. That's our dissolved oxygen. Here it is at 8 parts per million, but then right past the source of pollution, the oxygen is dropping. That's why we call it a sag curve, oxygen sag. We see the oxygen sagging down. So the oxygen's dropping, but then as we move further away from the pollution and it gets more and more diluted, we end up having a recovery. So the oxygen in blue has sagged, oxygen sag curve. Now remember, BOD, biological oxygen demand, we want that to be low. So here it is, nice and low. It's very clean upstream from this source of pollution. But then when we hit the source of pollution, this jumps up high. We end up with a very high biological oxygen demand here because the bacteria are breaking down whatever that sewage was, whatever was in that polluted source. And then as we move further away, further downstream, we see the BOD is dropping little by little until it's recovered at the end. And you can see what happens to the type of wildlife that can live here. Trout and perch and bass. Then we have carp and gar. Then we don't even have any fish where it's really bad. And then the carp can recover, the gar. This is the gar right here. We don't have those here. Those recover, and then we get trout and perch and bass again. Meanwhile, for invertebrates, mayflies and stoneflies, they need very clean water. But leeches, sludge worms, fungi, and bacteria, they don't need that clean water. So we find lots of them there. And then we see, again, the return to the mayfly and stonefly. So one field trip I like to do is we go to a creek and we look to see what kind of invertebrates are there. It's kind of hard to find fish in the creek, but it's usually pretty easy to find mayflies and stoneflies, sometimes leeches. So we like to use those as an indication of how clean the water is. If we find mayflies and stoneflies, we call those indicator species because they indicate clean water. Leeches are also indicator species, but they're generally indicators of not so clean water. And then we can look at water pollution and its impact on different habitats. So each of these different water sources has different problems with water pollution. So we'll start with the rivers and streams. So basically what they're saying is developed countries have reduced point source pollution. We've gotten rid of this problem for the most part, but we still have an issue with non-point source pollution in the developed countries. In the developing countries, we still have problems with sewage and industrial wastes. So how about that river? Do you want to go for a swim? Do you want to go kayaking there? This is in China. Although, you know, this is only a change in the last couple of decades. For instance, there's a river near the Great Lakes in the US that was so badly polluted before we passed the Clean Water Act. It was so badly polluted that the river itself caught fire, which is crazy. But probably on the surface of this river, for instance, there's lots of oil and gas and other flammable materials that could catch fire. And that's what happened to this river in the 70s. Let's see. I'm going to skip past the Ganges River, a sacred river to the people of India. And they bathe in it, they drink in it, they have religious ceremonies in it, but it's also very polluted. Okay, lakes. Now, while we talked about the oxygen sag curve and how the river could recover downstream from the pollutant, with lakes it doesn't work quite as well because there's less mixing, there's less current to mix up the water. And there's not so much flow. So that means that we can have these pollution problems build up in a lake or build up in a single bay next to the lake. And we have this issue with nutrients getting into a lake, which we call eutrophication. When we add nutrients to the lake, we say it is now eutrophic. And when we eutropficate a lake, the nutrients grow, and that allows the algae to grow faster, so we call it an algae bloom. And then as the algae are dying off, because they're reproducing very rapidly, but they have a short lifespan, so even though their population is going up and up and up, there's also lots of them dying at the same time. So we have a buildup of dead algae, which means the bacteria of decay are going to come in. They're going to use up oxygen out of the water. They have a high BOD, a high biological oxygen. And that lowers dissolved oxygen, and that's hard on some species like trout. That's exactly what we're trying to avoid with Lake Tahoe, is adding nutrients to the lake. And that's why we pump all of our sewage out of the lake. Here's our definition of eutrophication. Adding nutrients to a lake. Could be from runoff, it could be from sewage, could be from fertilizers, and if it's coming from people's actions, then we call it cultural eutrophication. And this is an interesting statistic. By far, most lakes near people in the US have eutrophication going on, cultural eutrophication specifically. Eutrophication is a natural process, but it usually takes thousands and thousands of years. But we saw before we passed the Clean Water Act that these lakes that were next to large human populations could become eutrophic very rapidly, especially if we were pumping sewage into them in addition to runoff. So that's when we passed many laws preventing putting sewage, at least untreated sewage, into these lakes. And now a lot of them have become cleaned up, but we still have the problem with runoff, carrying nutrients from fertilizers, from golf courses, from people's lawns, stuff like that. Okay, that's it for lakes. Groundwater. So groundwater can be polluted, even though it's underground and we can't really get to it. We can pollute it. So I guess we can get to it with a well, and similarly, you could inject materials into it with another well, but that's not what we're talking about here. We're just talking about chemicals that work their way through the soil, down through the pore spaces in the rock, and eventually end up in the aquifer underground. So by far, most of our drinking water in the US is coming from groundwater. Well, maybe not by far. Half of the US is from groundwater. If you're in a rural area, you probably have your own well. And so you need to make sure that your groundwater is staying clean and pure, because there's no way to clean it up after the fact. Once it's polluted, that's it. So for this reason, if you live out in the middle of nowhere and there is no sewage system, you probably have a septic tank, which all your pollution goes into this tank that's on your property, and every now and then you have to have it pumped out. But basically, the water that overflows from the tank is already underground, and that might be really nice to help your plants grow right there, but you wouldn't want your well right next to it. You would want your well far away from your septic tank. Okay, so here they're showing a diagram of some ways that the underground water can be polluted. They're showing these red arrows, how the water can get into how the pollutants can get into the groundwater from any of these sources. From a landfill, from a sewage line that's leaking. Here's the well that we're pumping water from for these houses, and yet here's their sewage line leaking into that very well. That doesn't look good. So there's a variety of sources of groundwater pollution, and it's very difficult to clean. One of the biggest ones really is gas stations. So gas stations have underground storage tanks of gasoline, and if that storage tank is old and has started to corrode, then gasoline can leak into the groundwater, which would then end up in people's drinking water, or could work its way downhill into a lake. So sometimes you might see a gas station that's closed off and they're digging it all up. That's because they're doing some work on that underground storage tank. And there are people that test that. They're part of the state Environmental Protection Agency, and they test to make sure that your gas tanks are not leaking into the soil. Okay, so it takes a long time for groundwater to get cleaned up, and there's two different kinds of wastes we're thinking about. Three different kinds. First, those that are degradable, the ones that break down over time. This would include sewage is degradable. It breaks down, given enough time, it'll break down. Bacteria will take care of that sewage problem for us. But then there are other materials that are non-degradable. They never break down. They are permanent. So lead, for instance, which is toxic, and arsenic, and other materials, if they get into the water, they are there permanently. And then we get a kind of in-between category. Some break down slowly, like the pesticide DDT, and they can pollute the water for decades. All right. Oh, this is showing the leaking gas tank that I was talking about a minute ago. So here's a leaking gas tank at our gas station, and it kind of has this plume of gasoline. So even underground, gravity is acting on the liquids that are in the rock and in the soil and pulling them downhill. And so the gasoline plume is going in this direction and not to the left because it's working its way downhill. Here we are showing some fumes are actually getting into these people's house. So this is gasoline fumes getting in there, even though it's not, the liquid gasoline getting into their water. But here we have a well, and it is taking up gasoline into their drinking water. I'm going to move past this one. And I'm going to move past this one too. This is an example of arsenic in the groundwater. It can naturally occur at high levels, so we have to be careful about where we're getting our drinking water from. And as usual, if we look at different solutions for this problem, which one do you think is cheaper and more effective, to prevent the pollution in the first place or to clean it up after it occurs? Well, as we've seen over and over again, usually preventing the problem is more affordable and it works better than trying to clean it up after the fact. Okay, finally we have ocean pollution, which usually we're not talking about polluting the entire ocean, we're talking about polluting patches of it. And this is often going to be a problem near a populated area. And we're going to include estuaries as part of this study, where the river meets the sea. This is often a place where people like to live because an estuary is a great place for ships to come and either load or unload their contents. So people often live in estuaries like the Bay Area. The Bay itself is a giant estuary. Another one is Chesapeake Bay on the East Coast, a huge estuary. And so these are often threatened or impaired by people. Here are 4 different pollution problems in the oceans. First, we have a dead zone. And I mentioned that the other day where we talked about the Mississippi River, where it reaches the Gulf of Mexico. It's bringing so many pollutants from such a widespread area across the country that we have a dead zone at the mouth of the Mississippi. When we say dead zone, that's because there's very few living things there because of the low dissolved oxygen. So the Mississippi picks up fertilizers and sewage from all across the Midwest, carries it to the Gulf of Mexico, and where it reaches the Gulf of Mexico, there's kind of a underwater zone where there's lots of nutrients, fertilizers, and sewage. And this means the bacteria build up, and once again, we have this whole cycle of the bacteria using the oxygen out of the water. So that's why we call it a dead zone, very low oxygen, and not many living things can survive that low oxygen. The next one is called a red tide, and the water can actually look a little bit red in this case. And it's not like it comes in at high tide or out at low tide. What's happening is where pollution has built up in the ocean, it can cause a bloom in a specific algae, which is a reddish colored algae. And this algae is called a dinoflagellate. And the problem with the red tide is that it actually is toxic. So this particular algae, the dinoflagellate, well, dino, like dinosaur, means terrible. Dinosaur means terrible lizard. Dinoflagellate is terrible algae. And these guys are terrible because they produce toxins, and that can hurt people and wildlife. In particular, what happens with dinoflagellates is that clams and oysters and scallops, these kinds of creatures are filter feeders, and so they feed on these algae, and the toxin builds up in the clam or the oyster or the scallop. And then if people eat that particular clam, then they're going to get exposed to high levels of the toxin and they're going to get sick. So a red tide warning means don't eat the shellfish from that area because they have accumulated lots of these dinoflagellates, which are filled with toxins. And the dinoflagellates bloom when there are pollutants in the water. Next, we have issues with oil spills. We've talked about the BP spill in the Gulf of Mexico. We talked about the Exxon Valdez. There's also a very famous one off the coast of California in Santa Barbara and thousands of others. And these can directly kill wildlife. They can cause damage to infrastructure. They can cover beaches with oil and tar. And finally, we have garbage patches, which we've also talked about quite a bit, I think, where we have all this floating debris, mostly plastic, and it gets concentrated in these gyres where the currents spiral around. They concentrate all that garbage. So here's a diagram showing these different kinds of problems. This is what we want to see, right? Lots of oxygen, the right balance between plankton and algae and fish. Here's a picture of that dead zone that we talked about off the coast of Louisiana, where the Mississippi reaches the Gulf of Mexico. We have this low level of oxygen. This would be the dead zone. And it changes in size depending on the season, the amount of water coming down the Mississippi, things like that. We talked about the Chesapeake Bay previously, where these pollutants are coming in from multiple states. You can see that the bay comes to basically here, but its watershed goes way up to here. So even in New York, any pollutants in the runoff from up here or that are getting put into these rivers, they make their way down into the Chesapeake Bay. And you can see even there's places with no oxygen. That would definitely be a dead zone in that estuary. Okay. So oil pollution in the ocean mostly comes from spills on land, although the dramatic ones are when a big oil tanker ship runs aground and leaks, or we have one of those offshore oil rigs leaking. Those are huge, but more commonly we have oil coming from the land and just adding and more to the ocean. Here there looks like they're cleaning up a bird. Yeah, she's holding its beak, and she's actually using soap to get the oil out of the bird's feathers in the hopes that it can be returned to the wild. This is a little map that I've found showing locations of different oil spills in 1 year. There were that many different oil spills around the world. I don't think much has changed, even though that was 30 years ago. So here's a comparison of solutions, preventing versus cleanup. As usual, prevention is probably the best approach. And I think this is going to go through some ideas of how to reduce pollution and prevent it. What can we do? One thing we can do is work with the Clean Water Act. Lately, for the last couple of years, the Clean Water Act has been weakened by the current administration. So pollutants in the water are being allowed. Basically, our pandemic also is giving polluters an opportunity to request that the regulations be waived. And that has been approved in many cases by the current government. Let's see. This is a diagram of how a septic tank would work. So if your house is not connected to a sewage pipeline, you would have a septic tank. Many homes here at Tahoe used to do this, but now we want to get it all out of the basin. Basically, when you flush the toilet or run the sink, the water goes into this big underground tank right here. And it just sits there, and the heaviest stuff sinks to the bottom, and the lightest stuff floats to the top. And then on the other end, there's a pipe that takes the overflow water out to what they call the drain field. So it's having a chance to break down naturally here. Often people put enzymes and bacteria into their septic tank. Like I lived with a septic tank for many years, and we would flush enzymes down the toilet every month to help break down the wastewater more effectively. And we never had any problems. And then the water would go out to a drain field. And basically you're adding nutrients to the soil at that point, and hopefully the plants are going to use those up instead of allowing them to get carried downhill to a body of water. We already looked very closely at sewage treatment last class. I'll just remind you that primary level of treatment is physical processes like screens and allowing the heavy stuff to sink to the bottom. Secondary is biological treatment, using bacteria usually to break down those wastes and convert them into simple molecules. And sometimes there is tertiary treatment, which uses a variety of activities. They could be physical, they could be chemical, they could be biological to further break down the sewage. And then finally, we chlorinate the water to kill all bacteria. And then we have to actually unchlorinate it afterwards before we put it back in the environment. We've talked about this already. This is an example of where we could have one of the problems if you're bringing the sludge from a sewage treatment plant to a farm. It could then run off into the water if it's not treated effectively. Okay. So then we also need to treat our drinking water, because we're getting our drinking water from an open body of water, whether it's a lake or a river, or even if it's groundwater, it can be polluted with various things. And so we have to clean up that water before we start drinking it. So there are laws to provide safe drinking water to people, at least in developed countries like ours. And this is one reason that the water that we have here at Lake Tahoe in our taps is very clean. It's not always the case, but for us, it's very clean, and there's really no need to be buying bottled water when you're up here at Tahoe because the water is so good. So it actually turns out that some bottled water is not even as clean as tap water. Some bottled water, basically, they just turned on the tap water and bottled it. And so this has led to a new problem where we have all this plastic that's being thrown away. So we were trying to work with this problem up here at the lake and combat the problem before the school shut down. We were doing some things with Turk to try to promote using less bottled water and using more tap water. One of the problems that people might have with drinking tap water is that sometimes it has a chlorine flavor, and that's because we put chlorine in that water to kill the bacteria, but it's easily removed by running it through a filter. So, for instance, I get my water out of the refrigerator and it runs through, it's tap water that comes through a filter before it comes out the door of the refrigerator. And so it doesn't have a chlorine taste. And if you don't have that kind of refrigerator, there's simple filters you can buy, like a Brita filter that has a filter built into a pitcher, and you just fill up the pitcher with water and it filters it as you're pouring it out, and it totally gets rid of the chlorine. It works great. All right, And that's it.